One of the most frequently used subroutine in a task involving a higher dimension data is near rest and neighborhood search, and that is goes under random projection. In the nearest search, nearest neighboring search, we are given a database of n points in RD dimension, where n and d is very large, usually large enough. The database can be proceed and store in the insufficient data structure, and thereafter we present a query of points in RD and are to find out the nearest approximate database point to that query point.
Excuse me, sir.
Yes.
Oh, nothing, sir. I was saying that someone wants to join.
Okay. Since the number of queries of often large, a query time to be answered is a single query. That means if your query is often very large, what will be the query time? Query time means a time to answer a single query should be very small. It should be very small. Otherwise, it will take a lots of time to give you output. And where processing time could be a very large if it is a polynomial function of d. And for this and other problems, dimension reduction. So that's why the problem of dimension reduction is very useful. And one project that data point k time dimensional space with the k is list very small than d usually depends on this k is usually depends on log d, can be useful for long as well as relative distance between the point approximately preserves. That means if you have rk space and rd space, whatever the distance between 2 points in this rd, so if I can say points, then a distance of the points will be this one, distance between two vectors, I can say, that will be preserved in this space. So for that we need to define what is a random projection, and that we have already discussed in the previous lecture also. Let us recall what was that concept, because based on that we have to discuss two theorems here. So the random projection, as we have talked in the previous lecture, is a function. So define a function f from rd to rk and will pick up a k points, or I can say vectors. So define this function f of v bar. F of v bar is equal to, so it is function, this v bar, it is in rd, you have to present that is in rk. So that means this is a vector, it is in rk. So that vector we are defining as u1 dot, this is a dot product between u1 and v bar, u2 bar dot v bar up to uk bar dot v bar, where this is true for every v belongs to rd, and where this u1, u2, uk are linearly independent vectors which can be pick up from the Gaussian distribution in RD space. So where this k vectors u1, u2 up to uk independent from the Gaussian distribution, that is 1 by 2 pi raised to d by 2 exponential of minus mode of x bar by 2. Then we have to prove this function f is a linear function. I have given you that is as an exercise. If anyone have tried for that, that's fine. I will prove that this f function is a linear function. And we already discussed that if T is a map from V to W, if I can say that this T is a linear map from vector space V to vector space W, if it satisfies the two conditions, that is T of V plus W is equal to T of V plus T of W. Another condition is T of alpha V is alpha times T of V. That means this T is preserves the vector addition and the scalar multiplication. So here our objective is to prove this function f is a linear function. So for that I will take two vectors for any v bar and w bar, it is in RD, and alpha beta belongs to f, where f is a field. Usually it is R here because the space is RD. Now we'll start with f of alpha v bar plus beta w bar. We'll have to prove that that is equal to alpha times f of v bar plus beta times f of w bar. So to do this, we'll apply this function. The function is defined like this. So u1 bar dot v bar. Instead of v bar we have here, it is this. So it is u1 bar dot alpha v bar plus beta w bar, u2 bar dot alpha v bar plus beta w bar, up to so on uk dot alpha v bar plus beta w bar. Now this dot product and this addition is distributive, so that's why I can rewrite this one as alpha times u1 dot v bar plus beta times u1 dot w bar. This is alpha times u2 dot v bar. So here we have also taken this alpha out and beta out. That is beta times u2 into w bar. Alpha and beta are the scalars as we have defined here. Up to so on, you will have uk dot v bar into alpha plus beta times uk dot w bar, and then you separate these vectors. So you will have alpha times u1 bar v bar, u2 bar v bar, up to so on uk bar v bar. plus beta times u1 bar v bar u1 w u1 bar w bar u2 bar w bar upon up to so on uk bar w bar. So this is alpha times f of v bar plus beta times f of w bar. So therefore we can say that this f is a linear map. So ultimately what we need to prove is f is linear, that we have done. Now the projection f of v bar is the vector of a dot product of v bar with ui's. It's every component of this one will be this, and we will show that it's very high probability that modulus of f of v bar is approximately square root of k into mod of v bar. What does it mean? If we can prove this one, what we can say is for any vector v1 bar and v2 bar in Rd, f of v1 bar minus v2 bar, as f is linear map, we can write down this is f of v1 minus f of v2 bar. And thus to estimate the distance between any two vectors in the space Rd, and we know that the distance between two vectors can be written as mod of v1 bar minus v2 bar. So it is sufficient to compute this f of v1 bar minus v2 bar is same as mod of f of v1 bar minus f of v2 bar. So as we have proved this one, that means a distance in, this is in RK space, you just see that this is in RK space and this is in RD space. So it's saying that the distance in RD space is same as the length of the vector in RK space. And since it is a linear map, and using, if that one is true, we can say that f of v bar minus v1 bar minus w bar is equivalent to square root of k v1 minus v2. So that means this is a distance between two vectors in Rd, and this will be the distance between two vectors in Rk due to this. So ultimate goal is to prove this statement. That means there is a high probability that in the random projection the distance is preserved between two spaces. Okay, so for that we have very important result that is known as a random projection theorem. This theorem, let me state what is this theorem state. Let v bar be a fixed vectors in Rd, and let f be defined as above. That means f, which we have defined already, that it is a random projection map. Then there exists a constant c greater than 0 such that for epsilon which is between 0 and 1, that means the value of epsilon, you can pick any value between 0 and 1, probability that mod of f of v bar minus square root of k mod of v bar, that means you can just see that what we are talking is the distance here is equivalent to distance here. So that is a difference we have here. So this probability greater than or equal to k times square root of epsilon into square root of k times mod of v bar is less than or equal to 3 into e power minus c k epsilon square, where this probability that we have taken here is taken over the random points which we are drawing of the vectors u bar, ui bar is used to define f. So whatever the u1, u2 up to un we have used to construct f, this probability is taken over that random points. So let us try to prove the statement. So by scaling both sides by mod of v bar, so that means here if I divide by mod of v bar, then we may assume that mod of v bar is 1 because we can scale that vector. So by scaling both sides by mod of v bar, we may assume that mod of v bar is equal to 1. Then the sum of independent normal distribution or normally distributed real variables is also a normally distributed. Where the mean and variance are the sum of individual mean and variance. So it's saying that e of x plus y is equal to e of x plus e of y. It is actually saying this, that sum of normally distributed real variable is also normally distributed, and the mean and variance is the sum of the individuals. So the sum of this individuals will be gives me the mean of that, and the same true for a variance also. And if x and y are normally distributed, then x plus y is also normally distributed. Okay, now I'll take this ui. See, ui is I stands for 1, 2, 3 for any I running from 1 to up to k. ui. So I want to write down what are the components of ui. ui, it is in RD space, that you can see in the definition of this. We have defined this ui, it is in RD space, and that can be picked up from the linearly independent from the Gaussian distribution. So that's why this ui I can take out as ui1. This is the first component. ui2, it is the second component. Up to so on. uid, it is a d component. So this is a component. Now let us see what is ui dot v bar. ui dot v bar, if I can say v bar is v1, v2 up to vd. V bar is also an element of RD. So that's why its components are v1, v2 up to vd. So if I take the dot product of these two vectors, then it will give me ui1 v1, ui2 v2 up to so on uid vd. That can be written in the sort or in the summation notation I running from 1 to d ui vj. So that can be written in for every I. So this is j running from 1 to d uij vj. Okay. Now this ui dot v bar has density and mean is 0. Variance is equal to so the random variable ui bar. So this is ui bar dot v bar has Gaussian density with 0 mean and a variance is equal to j running from 1 to d vj, which is mode of v bar square is equal to 1, because we have scaled them. A modulus we have taken it as 1. So due to this argument, that means this statement we have written here, and if you can say the a mean, if you want to calculate the mean of this one, that is expectation of this, each of ui has expect means mean is 0. So that's why each individual has mean 0. So that's why this mean of this one is also 0. And the variance, that is the variance of this one, is the variance of each individual, and that will be equal to the variance of ui is we have already taken it as 1. So that's why it is a variance of v1, variance of v2 up to variance of vd, but that is equal to 1 due to this. That if you want to see this one, then you just see that Why it is happening? Because of variance of vi dot v bar. That is, I can write down mode of, because you know that uh, variance of c into x bar is c square variance of x, that you probably know. So that is a mode of v bar square into variance of ui, but variance of ui is already is 1, or I can say it is a summation using that notation, that is I running from 1 to d vj square into variance of uij, but summation, so this is mode of vi square and the variance of uij is already 1, so that's why this is 1. So as I told you that variance of this each individual will gives me the variance will be 1, so that's why it is there. Now in the previous lecture we have talked about the Gaussian annulus theorem. Is anyone remember the statement of the Gaussian annulus theorem? Because we have to apply that Gaussian annulus theorem here. Let me recall what will be the Gaussian annulus theorem. This we need to use here. It says that for d-dimensional space, d-dimensional spherical Gaussian with unit variance in each direction for any d which is less than or equal to square root of d, all but at most 3 e power minus c beta square of the probability mass lies within the annulus square root of d minus beta less than or equal to mode of x bar less than or equal to square root of d plus beta, where c is a fixed constant, positive constant. Okay, so this is a Gaussian annulus theorem, and we have here d-dimensional data is there. We have here it is d-dimensional data, and everything, it says that the everything, that is, what does it mean of this last statement? The probability mass lies within the annulus. That if I can write down in terms of probability, then that we can write down as probability of mode of x bar minus mode of d, the whole modulus is greater than or equal to beta is less than or equal to 3 times e power minus c beta square. So this statement is says that beta is less than or equal to square root of d. This statement, because you just see that when you have mode of x minus a is less than delta, then we can write down this as minus delta less than x minus a less than delta. So if I add them one, it is a minus delta less than x minus a plus delta. So that's why due to this is the things we have given here. Here a is square root of b, delta is b, which we have. So that's why this quantity we can write down into this form. And it's saying that for each beta less than all but at most this much probability of mass lies within this. So that's why this is greater than, which is outside that annulus, is less than or equal to this much. Now here we need to apply the Gaussian distribution, sorry, Gaussian annulus theorem for f of v bar, and the value of this beta that we are taking here, that means we are taking beta is equal to epsilon square root of k is there, value of beta is this much. So if I can, and the value of x bar, it is f of v bar, x bar is f of v bar, this is the square root of b, because here it is the square root of d, and the value of d we can have, instead of d we have k, so that's why we give, this will gives me that probability of mode of f of v bar minus square root of k, the mode of this is greater than or equal to epsilon into square root of k. Instead of d we have k, because this things is in k dimensional space, is less than or equal to 3 times e power minus c into epsilon square k. But we have taken this mode of v is 1, so if I can multiply that, or I can scale them by mode v bar, so this is equivalent to write down the probability of mode of v bar minus square root of k into mode of v bar is greater than or equal to epsilon square root of k into mode of v bar is less than or equal to 3 times e power minus c square, sorry, c epsilon square k, and that proves this random projection theorem that we have started with. Now the random projection theorems establish the probability of the length of the projection of a single vector differing the significant from the expected value is exponentially small in k, and the dimension of the target space by union bound of probability of, of order n square pairwise difference, that is mode of vi minus vj, along with n vectors, that is v1 v2 up to vn, differ the significantly from their expected value is small, provided that k is greater than or equal to c upon, sorry, 3 upon c epsilon square ln n. Thus, the random projection preserves all the relatively pairwise distance between points in the set of n points is the high probability. And what I have talked here is actually a Johnson-Lindenstrauss lemma, which tells you that the distance is preserved in between the d-dimensional space and the k-dimensional space. So that is another theorem, but that theorem is known as Johnson-Lindenstrauss lemma. which says that for any epsilon which is between 0 and 1 and any integer n, let k, value of k is less than 3 by c epsilon square ln, where c is a fixed positive constant. For any set of n points in RD space, the random projection f from RD to RK defines as above. That means we already defined what is the random projection here. Defines above has the property that for all pair of points Vi bar and Vj bar with probability at least one minus 1.5 by n. So that is 1 minus epsilon square root of k mod of Vi minus Vj is less than or equal to mod of f of I minus f of j is less than or equal to 1 plus epsilon square root of k mod of Vi minus Vj. So it is exactly the same things which we have discussed into the random projection theorem. Because if you can just compare with the random projection theorem, if you replace that value, so in the random projection theorem, what we have here, it is V bar. So instead of V bar, if you just write down Vi minus Vj, then we can able to write down this statement because everything is satisfies there. So what I am saying that, let's discuss the proof for that. For any fixed Vi bar and Vj bar, by random projection theorem, we say that the probability of mod of f of Vi minus Vj, mod of this minus square root of k mod of Vi minus Vj is greater than or equal to, instead of writing epsilon, I'm just writing 1 plus epsilon. 1 plus epsilon square root of k mod of Vi minus Vj is less than or equal to 3 times e power minus ck epsilon square. And what does that mean? This means that For any fixed Vi minus Vj, the probability that this is outside the range of, that means outside the interval. So I'm talking about mode of x minus a is less than epsilon. Then what will be the outside this? That is this is written is greater than or equal to. So if you want to say it is less than or equal to, then it is the a minus epsilon to a plus epsilon. It is between this interval. Okay, so outside this interval is happening this thing. So what we can say is for any fixed Vi and Vj, the probability that mode of Vi minus Vj is outside the range one minus epsilon square root of k mode of Vi minus Vj to 1 plus epsilon square root of k mode of Vi minus Vj is at most 3 e power minus c k epsilon square that we have here. And since the value of k here it is taken is less than 3 by epsilon square ln, this will be less than or equal to 3 by n cube. Why? Let me see this. Because we have 3 e power minus c k epsilon square. We have already that is less than or equal to 3 by n cube. So this n is 3 is cancelled out, which is equivalent to write down 3 sorry e power minus c k epsilon square is less than or equal to 1 by 3 cube, which is equivalent to write down n cube is less than or equal to e power c k epsilon square. If I take n cube here, this is minus, so it is 1 upon that goes on the other side. If I take ln both sides, so this is ln raised to 3 is less than or equal to c k epsilon square ln of e, but ln of e is 1, ln of n cube is 3. So that is gives me the value of k is greater than or equal to is 3 into ln of n upon c epsilon square, which is exactly the given condition for k. Okay, so that's why we have this. And since there are NC2 possibilities, because we have taken a points Vi and Vj, so there are n points we have to taken, and picking out of n points, the possibilities of picking out 2 points is NC2. So there are NC2 which is equal to n into n minus 1 by 2. I can say that is less than or equal to n square by 2 pair of points by union bound. What do you mean by union bound? That is the probability of union of ai is less than or equal to probability of summation of that is less than or equal to summation of probability of ai. That is known as a union bound. So since there are this many n square by 2 pair of points, and by union bound, the probability of that any pair of any pair has a large distortion is less than 3 by 2n. So that is 3 by 2n, which can be get from here. This is less than or equal to 3 by n square, and that is, we can say, that is multiply with union bound. So this condition is true for any pair of points. So there are n number of points, and every time if you use this summation of probability of all the points here, that will be less than or equal to summation of probability of each pair. But each pair is less than or equal to 3 by n square, n cube. And so what I can actually, you have probability of that quantity is less than or equal to summation of the probability of every pair is there. But for every pair we have a probability is 3 by n cube. And how many such possibilities? This summation, so that is equal to summation 3 by n cube. But this summation is possible for NC2, that are NC2 terms will be there. That I can say it is less than or equal to n square by 2 terms will be there. So this summation is actually running from 1 to n square by 2. So, and this is independent of I. So that's why it is equal to 3 by n cube into n square by 2. And this n square will cancel out. So that will left with 3 by 2n. So that is the exactly 3 by 2n is 1.5. So exactly the theorem is saying is the same thing. It says that for all pair of points vi minus vj with the probability at least 1 minus, so it is, we have proved for at most, so at least will be 1 minus that, because the probability is 1 minus 3 by 2. This is 1.5 is nothing but 3 by 2n. So that proves the Johnson-Lindenstrauss Lemma. And that's it for this random projection we have. In the next, we need to discuss regarding separating a Gaussian. Okay, that we'll discuss in the next lecture. So if you have any doubts, you can ask.